Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's logic lesson, we will be learning about disjunctive inference. So here's the do now. For number one, let P be the statement it is 9 a.m. and Q the statement it is morning. What is the converse, inverse, and contrapositive of if P then Q? And secondly, other statement if P then Q and not P or Q logically equivalent. Why or why not? So for number one, let's first write the conditional statement if P then Q. And the best way to do this is to organize this in a table again. So the first statement for the conditional statement if P then Q is if it is 9 a.m., then it is morning. So obviously this statement is true, right? So let's write out the inverse, the converse, and the contrapositive now. So the inverse would be if it is not 9 a.m., then it is not morning. Why is this statement uncertain? Well, because if it's not 9 a.m., it could be, for example, 10 a.m. and it is still morning. Or if it's not 9 a.m., it could be, for example, 1 p.m. In that case, it is true that it's not morning. So this statement could either be true or false depending on the situation. So we're going to write uncertain for this one. So let's write the converse now. So the statement would be if it is morning, then it is 9 a.m. Is the statement true, false, uncertain? Well, again, if it's morning, it doesn't necessarily have to be 9 a.m., right? It can also be 10 a.m. This statement is also uncertain. Okay, so finally, let's write the contrapositive. So the contrapositive would be if it is not morning, then it is not 9 a.m. And again, this statement has to be true, right? As we learned last time, the conditional statement and the contrapositive are logically equivalent, meaning that if the conditional is true, the contrapositive must be true. But if the conditional is false, then the contrapositive is false as well. Okay? So that's basically the summary of what we did in the previous lesson. Okay? So now for number two, are the statement if P then Q and not P or Q logically equivalent? Why not? So how would we be able to check if these are logically equivalent? By simply constructing a truth table. Okay, so here's a truth table that we have set up. Now let's first complete the third column here, the conditional statement between P and Q. And here we have true, false, true, true, okay? What about not P? Well, all we need to do is just negate the first column. And here we have false, false, true, and true. And now we want to take the disjunction or the or statement between the not P, whatever's in the fourth column here, and the Q, whatever's in the second column, okay? So again, in the disjunction, at least one of them has to be true. So true, okay? So what about this one? We end up with false, okay? And then we have true and true, okay? So the question is the statement if P then Q logically equivalent to not P or Q? Well, if you look at the statement if P then Q in the table, we know the truth values are true, false, true, true. So let me highlight this. And then if you look at the statement not P or Q, the truth values are also true, false to true. So what can you say when you compare both truth values? That the truth values are the same. What does that mean? Well, it's indicating that we have some type of logically equivalent statement. Now, the best way to show that something is logically equivalent in the table is to add another column for which we replace this double arrow with a biconditional, okay? So let's do that really quick and see what the truth values will come out. Okay, so what are the truth values here? In the last column, so we have a biconditional, and we learned that in a biconditional statement, both statements have to be the same, either both true or both false. So here we end up with all true values for the biconditional statement, okay? So we learned that when everything is true, that's called a tautology. Okay, so that means that all truth values are true. And when you reach a tautology, that means you have proven something. That no matter what the values are, the truth values for P and Q, no matter how you scramble them, or no matter what the combinations are for true and false, everything is always going to be true. So in this case, now we can say that yes, the statement if P then Q and not P or Q are logically equivalent. Have you ever wondered who ever uses these laws of logic in real life? Well, it turns out that detectives or investigators use laws of logic to solve crimes. Let's say that a crime has been committed, for example, a murder. What do usually police officers do? Well, first they look at a list of possible suspects and start investigating. They investigate each possible suspect until the final suspect is discovered. So let's assume we have two suspects, okay? And let's call these suspects John and Mike. So far, we know for sure that John or Mike is the criminal. So we can actually write this as a disjunction, J or M. Therefore, the detectives have to investigate John and Mike's action. But again, since these are the only two suspects, it has to be either John or Mike, the criminal. So we have now the following condition, that John is the criminal and M, Mike, is the criminal. So therefore, we can actually combine these two as shown in the previous slide as J or M, okay? So that we actually call the premise. Now, a premise in logic means that it's always a given truth, okay? So it's actually something that is given and has to be true. So therefore, the statement will be John or Mike is the criminal. And again, we accept that to be true, okay? So what could be the possible outcomes here? Well, let's say that detectives discover that Mike is not the criminal. So how can we write this in logic using any logic operations? Well, we can just simply write it as not M, okay? So Mike is not the criminal. So that leaves us with what? Well, that leaves us with the conclusion to be J. John is the criminal. So notice here that the premises are both true and the conclusion must also therefore be true, okay? Obviously, if we would have investigated this and we noticed that John is not the criminal, then the conclusion would have been M. Now, the reason why I'm bringing this up, because this is actually a law of logic. And this law is called the law of disjunctive inference. So let me introduce you to the definition. So the law of disjunctive inference states the following. For number one, if a disjunction P or Q is true and the disjunct P is false, then the other disjunct Q is true. Okay, and you can actually see it here on the left side. And by the way, the three dots, that means therefore. Okay, so here we have P or Q, that is true. Not P has to be true, therefore Q has to be true. The second part states if a disjunction P or Q is true and the disjunct Q is false, then the other disjunct P is true. So basically, it's kind of like saying, okay, what if John is not the criminal, right? It's the same thing. There could be two different scenarios. So the second scenario says, okay, the first premise is true, which is P or Q. The second premise, not Q, is true. Therefore, P has to be true. So let's look at another example. What if we had not P or Q as our first premise, right? We know that premises are true, so we can write T over here, that is true. And the second premise is true, correct? So then what has to be followed here? What can we say here? What can we conclude that is also true? Well, in this case, we just say that Q is true, okay? And again, how do we know that? Because remember that in a disjunction, and let me actually use a different color so you guys can see it better. So let's say that in a disjunction, the disjunction is true, right? So we know in this case, P is true. So let me write the T over here. And what can we say on not P? Not P is false. Now, in order to make the disjunction true, at least one of the disjuncts has to be true. So therefore, this has to be true. And that's why we can say that the conclusion here is true, okay? Anyway, so that's basically it for today's lesson. Again, please post a comment if you have any questions. Don't forget to subscribe and hit the like button. Otherwise, have a wonderful day.